Okay, in this podcast we're going to talk about free energy. And I've added a few things here that are not in your notes that you can scribble in the margins or just watch, and the most important things are in the packet. Okay, so free energy has a symbol of delta G. It was discovered by a guy named Gibbs. That's why we sometimes call it Gibbs free energy. Free energy is sort of a misleading term. It's really the energy available to do work. Okay, so we say if a reaction is thermodynamically favored, then it is spontaneous. We used to use the term spontaneous all the time. The College Board is trying to move us to use the term thermodynamically favored. So let's continue here. So a reaction is considered to be spontaneous or thermodynamically favored if the Gibbs free energy change is negative or if it's less than zero. So thermodynamically favored, what that means is once the reaction gets started, it might need a little push, some activation energy hump to get over, then it's going to proceed unaided without any energy input. It doesn't tell us anything about rate, so a reaction could be thermodynamically favored or considered spontaneous. It does not mean that it is fast. Okay, it might be a very slow reaction and be thermodynamically favored. Okay. There are several ways to determine what delta G is. And one is delta G equals delta H minus T delta S. It's probably the most commonly used equation. And in a minute, I'm going to talk more about that. Delta G, we can use an equation that's just like Hess's law for entropy or enthalpy. And again, delta G of the reaction is equal to delta G products minus delta G of the reactants. Now, let me just, I don't think I explained this in an earlier video very much, but delta G does not means at standard conditions, which is generally 25 degrees C and 1 atm. So it's warmer. It's like room temperature. It's warmer than STP, which is 0 degrees C. Okay. You can also use Hess's law of summation, where we have the multiple reactions and we flip things around to get the sign right and all that other stuff, and add the equations together. And the last way, well, there's actually more than just this, but the other way is using this equation called negative RT natural log of K, which we call the Ratlink equation. So we're going to talk about each of these. So the first one is delta G equals delta H minus T delta S. So what I'm going to do is stop here and let Mr. Anderson, who does a really nice job of this, explain conceptually what this means, and then we'll take a look at a problem.
And welcome to my podcast on Gibbs free energy. Whenever I get to Gibbs free energy in the year, I can see my kids' eyes gloss over and they're confused. And even William Gibbs talks about this in this quote. He said, "The idea of entropy and the second law of thermodynamics will seem far-fetched and may repel beginners as obscure and difficult for comprehension." So what does that mean? I'm going to try to tackle something that's been a problem for years. I'm going to try to make Gibbs free energy more understandable, and so that you really know what it is and understand the power of it, especially in biology. And so I think the first place to start is the name itself. The idea of free kind of gets in the way. And so what I'd like to go back to is the old name, which it used to be called available energy. And so let's think of delta G as available energy, or energy that we can actually use to do work. The other thing that I think makes it hard is the equation itself is confusing. We've got delta G, we've got enthalpy, we've got entropy, we've got words that you're maybe not understanding. And so what I'm going to try to do is pare this down to the easiest explanation that I can, and then we can get into the more of the specifics a little bit later. And so the best place to start when you're trying to understand available energy or free energy is to look at spontaneous reactions. Spontaneous reactions are reactions that once you give them a little bit of a push, they'll actually go on their own. These reactions also will tend to release energy and they give energy to their surroundings. Quintessential example in life is cellular respiration. But let's not get there yet. So the three reactions that I'm going to talk about here are, number one, a ball rolling down a slide. Number two, diffusion. And then number three, a cherry bomb that's exploding. And so we're going to apply Gibbs free energy to each of these. So let's start with the ball at the top of the slide. And the ball at the top of the slide is going to roll down to the bottom. And so the first thing that I want to give you is what's called enthalpy, or total energy of a system. And so if we say this is a system, what happens to the total energy of the system as the ball rolls down the slide? Well, if you know anything about potential energy, the amount of potential energy that we have up here is going to be greater than the amount of potential energy that we have down here. And so the total energy of the system, we'll call that H, or enthalpy. The total energy of the system has gone from a big H to a little h. In other words, the total energy of the system has decreased when the ball rolls down. Now, if I had to push it up again, then we would add energy to the system. But this is a spontaneous reaction, and the enthalpy, or the total energy, is decreasing. Now, in biology, we don't move around because of potential energy or mechanical potential energy. In biology, our energy, or our potential energy, is actually in these bonds. In other words, there's a huge amount of potential energy in this bond between the carbon and the hydrogen. And so this right here is glucose. And if we can release some of that energy, we can do it to do work. And so again, what is H? H stands for the total energy of the system. And it looks like in a spontaneous reaction, that's actually going to get smaller or decrease. Okay, next one, let's talk about diffusion. So in diffusion, imagine that right here we've got a bunch of molecules in this container and they're bouncing around, and I remove this wall. So if I remove that wall, what's going to happen to the molecules? The molecules are going to spread out to fill that area. We call that diffusion. Now entropy is, we use the symbol S for that. Entropy is a measure of the disorder of a system, or sometimes we call that the randomness of the system. And so let's compare this. Right here we've got a bunch of molecules on this side, and then we've got a lot of space over here. So what happens to the disorder of that system as I do diffusion? Well, it's becoming more disordered. In other words, the entropy is increasing. What's an example of that? Let's say I go into your room and your room's a mess. It looks like this. If I say clean up your room, then you could go like that. And so what happens through diffusion, or in this spontaneous reaction? Well, let's say remove this wall. What's going to happen now? We're going to get even more disorder. So we're going to even get a bigger S value. And so in this spontaneous reaction, it looks like the S value is increasing. Okay, the last one is that cherry bomb. So let's say we have a cherry bomb. We put it on the desk. Does it explode? No. And one of the reasons it doesn't is the temperature is really low. And so let's say I add a bonfire to the situation, so I increase the temperature. Does that make it a more spontaneous reaction, or is the reaction more likely to happen or less? Well, it's more likely to happen if I increase the temperature, more likely to get an explosion. Okay, so those three things, total energy or enthalpy, entropy or S, and temperature can affect spontaneous reactions. And so now let's apply that to Gibbs free energy. And so before we actually get to the equation, let's just do a little algebra here. So let's say I wrote this equation, x equals y minus ab. Okay, so let's say we had this equation right here, and I were to decrease this value, the y value. What would that do to the x value? It would decrease it, right? Let's say I were to increase the a value and increase the b value. What would that do to the x value? Well, since we're subtracting right here, that would decrease it as well, or make it even go farther down. And so let's go back and summarize those three spontaneous reactions. In the first one, the ball rolled down. So what happened to our H value? Well, our enthalpy of the system decreased. What should that do to our Gibbs free energy, or available energy? It should decrease that value. What happened here when we increase the entropy of the system, or increase the delta S? Well, if we increase the delta S, that should also decrease the Gibbs free energy. So now we have two things decreasing that. And what happened here? Well, if we increase the temperature, that made it more spontaneous. So if we increase that, we also decrease the Gibbs free energy. So what's the moral of the story? Moral of the story is that if the delta G ever decreases, or if it's ever less than 0, that's a spontaneous reaction. Likewise, if the delta G is greater than 0, let's turn to the next slide, that's going to not be a non-spontaneous reaction. Okay, so in summary, if the delta G is less than 0, that's a spontaneous reaction, or we call that an exergonic reaction, or an energy-releasing reaction. If it's greater than 0, that's an endergonic reaction. And then finally, if nothing happens to the available free energy, then it's just at equilibrium. The quintessential example of a spontaneous reaction in life is going to be cellular respiration. Photosynthesis is an example of an endergonic reaction. And so
might feel like I'm beating a dead horse, but I can't tell you how important it is, how many times people make mistakes. Entropy values are in joules. Enthalpy and Gibbs free energy are in kilojoules. And you need to be careful about making conversions. So if delta G equals delta H minus T delta S, and this is in kilojoules, and this is in kilojoules, and this is in joules, you've got a problem. You've got to do a conversion. Okay? Alright, so here's one that involves a lot of work. Here we got the H should be an arrow again. So the reaction above was carried out at 25C. We need to calculate delta H, delta S, and delta G using this data. Alright, so we have data here we can use to calculate delta H, data here we can use to calculate delta S, and then we can use the formula delta G equals delta H minus T delta S. Okay. Alright, so delta H, it's going to be my products minus my reactants, right? And oxygen would be 0. I plug in the numbers and I get minus 198 kilojoules. I do the same thing with delta S, and oxygen's value is not 0 in this case, so I've got to add it in. And when I do that, I get minus 187 joules per mole. Note that delta H is in kilojoules, delta S is in joules. Delta G is going to be delta H minus T delta S. I change the T to Kelvin. Now the thing that I do here is I just take that value in joules that I had here and I say times 10 to the minus third kilojoules. Okay? And when I do that, I end up with negative 142 kilojoules per mole.